In this video, we're going to look at another type of a MM1 system, which is MM1 GDC infinity. So it's the C that makes a difference with the previous MM1 that we've seen. So the C here means that our system has only the capacity to handle at most C customers, which include the customer who is in the service. For example, if C equals 8, it means that our system can only handle at most 8 customers. After we have 8 customers in the system, we cannot accept any new customers, and then any new customers cannot stand here to form a queue. So it says that when C customers are already in the system, all arrivals, all customers are turned away and forever lost to the system. They must go away because there is no place for them to stand behind the queue. Now here's the rate diagram for MM1 GDC infinity. For the lambda, it's all the same lambda until up to the state C. Then we will have lambda C equals 0. Or in other words, we do not see any lambda going out from there. Okay. And then for the mu, it's all the same mu, except that for mu 0, it is equal 0, so we do not see any mu going out from the state 0. Now, the unique characteristic of this system is that even when the rho greater than or equal 1, in other words, even when the arrival rate lambda is greater than or equal to the service rate mu, this system will not blow up. Okay, because we have this C here as the maximum capacity of the system, then the queue will never keeps getting longer and longer, because the capacity of the system limits the queue just up to that number of customers. That's why in this case we will not have a blow up system, and the consequence is that for this system the steady state always exists regardless of the rho. For the steady state probabilities and for calculating the L's, we have different sets of formula. It depends on whether lambda does not equal to mu or lambda equals to mu. So here are the formulas for lambda does not equal to mu, and this is for lambda equals to mu. This is for L, and then there's the L. However, for LS and LQ, they are the same for both this and that. Now for determining W, we need to find out the arrivals or customers who actually succeed to enter the system. Okay, so we have the lambda, which is the original bunch of people who arrive at our system. So lambda is the original arrivals per unit time. But we know that in this system, some of the arrivals find the system is already full to its capacity C. So this group of people, they will be rejected by the system such that they are lost and they cannot enter the system. Okay, so people who find that the place is already full to its capacity, they will be lost, they will be rejected, they cannot enter the system. Now the probability of this system being full is pi c. Okay, because this pi c is saying that this is the probability that we have C people already in the system, which means that the system is completely full. And because this is the probability that the system is full, pi c, we can say that the arrivals or the customers who cannot enter the system is this pi c fraction of lambda. So remember, lambda is the original bunch of people that wants to coming into our system. But then there's a probability of pi c that the system is actually full and they will be rejected. So this portion of people, lambda times pi c, are the people who are rejected from the system because they find out that the system is full when they arrive. So now the arrivals who can actually enter the system is the original lambda minus lambda times pi c. So this is the proportion of people, sorry, not the proportion, but the number of people or number of arrival who actually enter the system. Lambda times 1 minus pi c. Now we may obtain W, WQ, and WS based on the L, LQ, and LS that we have obtained before. And then we use this little queuing formula to obtain the W's. Okay, so just divide the L or LQ or LS with lambda times 1 minus pi c. Now here's an example, and as usual, we'll identify the arrival rates, which is 20 prospective customers arrive each hour. And then about the service, it says it takes an average of 12 minutes to cut each customer's hair. And then we have one-man barber shop, so just one person, one server, I mean. And then it says we only have the total of 10 seats in the system. So those are the important information in this problem, and we're going to answer these two questions. As usual, first let us define the Candeli notation for this queuing system. It says that the inter-arrival times are exponentially distributed, and then the haircut times also exponentially distributed. So we got the first two and then it is a one-man barber shop. So we've got one here, and then GD queuing discipline. And then the system can only have a total of 10 seats. That's why we write down 10 here. And then infinity because there's no information about the population of this barbershop. Now, this is the lambda of 20 customers per hour. It is said the prospective customers because this is the bunch of people originally who wants to come into this barbershop. But we know that some people may be rejected from the system because the system is already full. And then same as before, we need to make sure that we have the mu or the service rate in the same unit with lambda, customers per hour. We are given this 12 minutes is 1 over lambda. We convert it into lambda, which becomes 5 customers per hour. And now rho is lambda over mu. It is 4. So the first question asks, how many haircuts per hour will the barber complete? So we notice that this is our system, and we have lambda does not equal to mu. So to find out how many haircuts that the barber complete, first we calculate how many number of customers actually entering the system. So this is the formula, lambda times 1 minus pi c, because we know that 20 customers wants to enter this barbershop, but let's see how many actually can really enter the system. So we need to find pi c, and these are the formula for the steady state probabilities. For pi j, we need pi 0. And then this is the formula for pi 0. We have got everything ready actually because pi 0 only needs the rho, and then we have got the rho over here. And then after we calculate pi 0, we may calculate pi 10 in this case. Okay, so this is the pi 0 and this is the pi 10. The reason we are calculating pi 10 because here we need pi c, and the c in this problem equals 10. Okay, so just plug in the numbers, and then we got this pi 10 equals 0.75. Now we go back to calculating this thing here, lambda times 1 minus pi c, and then here's the answer. So from 20 customers per hour prospective customers, only 5 of them per hour can actually enter the system. Now, the next thing is that we need to notice that pi 0 here is practically equals 0, which means that the barber is never idle because this barber is just by him or herself, and then the probability of having 0 customers is almost 0, which means that there is almost always at least one customer in the system. If there is one customer in the system, the barber must work. So we can say that because the pi 0 is practically 0, it means that there is always customer in the system. The barber is always working all the time. So the barber is never idle. He is always working, which means that the barber will work according to this maximum service rate that he or she can provide. So we will say that the number of haircuts that the barber complete per hour on average is 5 customers per hour. Because the barber again keeps working, so he or she will do as much as um, their maximum capacity of working, which is 5 customers per hour. On the average, how much time will be spent in the shop? How much time spent in the shop by a customer? Okay, so this is asking about the W. Here is the formula for W. We need to calculate the L first. This is the L. We have all the values that we need for rho and for C. Just plug in the number and then go back to W, and then we get the answer 1.93 hour. So that's all for this MM1 GDC Infinity, and see you in the next one. Thank you.